Hello again. In this video, I'm going to do an example where we use Rolle's theorem. So let's look at example 1. So in this example, we're supposed to find an interval I on which Rolle's theorem applies to this function, then find all the points C in the interval I at which f prime of C is equal to 0. So first, let me remind you of what Rolle's theorem says. So Rolle's theorem says that if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, with f of a equal to f of b, then there exists at least one point C in the open interval from a to b such that f prime of C is equal to 0. Okay, so this is the function that we're given. We're actually supposed to find an interval to apply to Rolle's theorem. So let's first find the interval that we're going to use to apply to Rolle's theorem. Now here's how we're going to find that interval. First thing I would do here is go ahead and factor this function. Notice you can pull an x out since x is in common with all three terms. And that's going to leave you with x squared minus 7x plus 10. And then you can factor this trinomial. You need two factors of 10 that add up to negative 7. And of course, that would be negative 2 and negative 5. Okay, so that factors into x minus 2 times x minus 5. Now, the reason I factored this is because it makes it a little bit easier to see what interval might work. Notice that if x is equal to 0 here, right, f of 0 gives you 0. So does f of 5. Right? So if we use the interval from 0 to 5, the closed interval from 0 to 5, then f of 0, f of the left endpoint, and f of the right endpoint, f of 5, are both equal to 0. So this means, f of a is equal to f of b. So this would be a good interval to use because we at least have f of a equal to f of b at the endpoints here. Okay, so let's use this interval. Now, let's verify that the conditions hold before we use the theorem. Before you apply any theorem, you should always check and make sure that you're satisfying the conditions before you reach the conclusion of the theorem. So, the first thing we need to check is to make sure that f is continuous on the closed interval from 0 to 5. Of course it is, because that's a polynomial. Polynomials are continuous everywhere. So in particular, this polynomial is continuous on this closed interval. We also have to show that it's differentiable on the open interval. From 0 to 5. Okay. Now, the reason that's the case is because, again, this is a polynomial. And polynomials are differentiable everywhere. So, in particular, this is going to be differentiable on the open interval from 0 to 5. Remember, differentiable just means the derivative exists. Okay, so if you really want to show this in more detail, you can go ahead and find the derivative. So the derivative of this function would be 3x squared minus 14x plus 10. And you can see that if you pick any number in this interval, you can plug it into the derivative and you're going to get a number out. So that means the derivative exists for every number on this interval, which means f is differentiable on this interval. Okay. Now the third condition that we have to satisfy is f of a must be equal to f of b, and we've already shown that. F of 0, f of the left endpoint is equal to 0, and f of the right endpoint is equal to 0 as well. So we've satisfied all three conditions of the theorem. So now we can conclude that there must exist at least one point C in the interval from 0 to 5, such that f prime of C is equal to 0. Okay, so then the next thing we're going to do is we're actually going to try to find at least one point C in the interval from 0 to 5 where the derivative evaluated at C is equal to 0. So how do we do that? We know one exists, right? By the theorem, there exists at least one such C value that it makes the derivative equal to 0, but how would we find it? Well, the obvious answer is to go to the derivative and set it equal to 0, and then find out when that happens. Okay, so let's set the derivative to 0 and then find out for which x values is the derivative equal to 0. Okay, so this is a quadratic. Normally, the first thing you would try and do is put it in standard form, which it is. Get one side to be 0. It's called standard form. And try and factor it. But if you try to factor this, it doesn't really factor. But that's okay. If it doesn't factor, you can always use the quadratic formula. So let's go ahead and plug that into the quadratic formula. Okay, so minus b, now notice b is a negative 14, plus or minus the square root of b squared, minus 4, a is equal to 3, and c is equal to 10, all over 2a, and a is equal to 3. Oh, I wrote this as x, it should be 2a. Okay, now, this obviously gives us 14, plus or minus, and then negative 14 squared is 196. This gives us 120. And of course, that's equal to 6. Okay, and then this would equal 14 plus or minus the square root of 76. All over 6. Then let's look at the square root of 76 and see if we can't simplify that. So I believe 76 factors into 2 times 38, then 38 factors into 2 times 19. Okay, so you can write 76 as 2 times 2 times 19. And then the 6 can be written as 2 times 3. Let's go ahead and factor the 6, because what's going to happen is, of course, this is going to give you 2 square roots of 19. And then this 2 is going to cancel with the 14 and leave you with a 7. It's also going to cancel with this 2 and leave you with square root of 19. And then, of course, the 3 is going to be left on the bottom. Okay, so these are the spots, right? These are the x values where this derivative is equal to 0, right? If you were to plug these into these x values here, you would get 0 out. But the question is, are any of these in this interval? Because the theorem guarantees that there's some point C in the interval from 0 to 5 where the derivative is equal to 0. So we should plug these into a calculator maybe to get their decimal values and see if they're in the interval from 0 to 5. Okay, so if you do that, you'll find that the two answers that you get are approximately 0.88 and 3.79. Of course, both of those are in the interval from 0 to 5. So the theorem guaranteed us the existence of at least one c value in the interval where the derivative was equal to 0. We actually found two of them. Okay, and you can see that from the graph here as well. This is the graph of the function that we were working with. The graph looks like this. And I think you can see that the derivative is equal to 0 at 3.78. And it's also equal to 0 at this point over here. And so let's go see where that's at. Okay, so it should be at 0.88 as well. Okay, so the theorem again guarantees us the existence of at least one value of c in the interval from 0 to 5 where the derivative is equal to 0, but it is certainly possible that there's more than one, and in this case there's actually two of them. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.